Hi, and welcome to Module 3 of Lecture 15. In the next module, we'll be dealing with the case of constrained optimization, in particular, the case of equality constraints. So that's the topic of the next two modules. In this module, we'll discuss the sort of underlying idea behind it, the conceptual intuition behind it, and the method which to use to do it. In the next module, we would do an example of constrained optimization, and there are more examples again in the book and so on. Okay, so first, why do we do this? So we discussed earlier in the first module of this lecture, oftentimes you have a constraint on your optimization problem. So if this is game theory or decision theory, you might have a budget constraint on your actions. You might want to buy everything in the world, but you have a limited sum of money to do it with. In that case, you have a constrained optimization problem. Or perhaps you have a constraint in that you can't have negative values of things. You can't donate a negative amount of money to a candidate, right? You can't steal money from that candidate in general. You can't donate a negative amount of money to a candidate. You can't put a negative amount of money into a public good. You can't, mobilize a negative military for war, right? All these things are positivity requirements, or probably non-negativity requirements, more precisely, and they prevent you from looking across the entire space of actions. Why is that important? Well, a non-negativity constraint says you can't have a negative number. But what if the thing is bad, right? What if you'd love to have a negative number? What if you're talking about, a number of, brown sites for environmental catastrophe, right? You'd love to maximize that by setting that number as small as possible, all the way down to negative infinity. You can't, so you're forced to have 0. So the maximum here would be 0, right? So in different cases, you get situations in which you don't want something, but you're forced to have at least 0. And in that case, the non-negativity constraint would bind you and be an issue. Another more common scenario we saw in the previous, in the first module of this lecture, talking about buying apples and oranges under a budget constraint. If you want both equally, you wouldn't want to buy at all the orange. In fact, optimally what you would do is sell tons of oranges at $2 a piece. So let's go back to the example again in case you've likely forgotten that. If your utility is equal to apples plus oranges, but apples cost $1 each and oranges cost $2 each, and your budget constraint would then look like this. Has to be less than or equal to some budget. Well, and that's an O not a 0. In that case, to maximize that problem by itself, ignoring the non-negativity constraints, ignoring the fact that apples can't be negative and oranges can't be negative, and again I'll put that for 0. If you ignore these two constraints over here, then what you actually want to do is sell all the oranges you can get your hands on, make $2 a piece for the oranges, and then buy a ton of apples with that money, right? That's the actual optimum. When you're constrained by the non-negativity constraints, you can't do that. At most, you can not buy oranges, so you buy apples only. So that's why these constraints would matter, and they affect the outcome of these decisions. And note, they affect them in an interdependent way, and that's important. Back when we first looked at constraints, without calling them constraints, back in part 2 of the course, when we had bounds on our optimization problem, we said, okay, x is between -1 and 1. That also put constraints on our problem, but they weren't interdependent constraints. They didn't affect anything else. They just said, look for the maximum x. If it's between -1 and 1, great. If it would have been outside of those bounds, then look only in this range, right? Then choose the bounds themselves potentially. So that we could do that because there wasn't any interdependence going on here. In more than one dimension, there is, right? What if you had an interaction term in your you're trying to minimize error, squared error, and your thing had an interaction term that looked kind of like this: x1, x2, x1, x2. But what if x were actually bounded? What if x1 were bounded by something? Well, then how much x2 you should have, for instance, how much weight over here on the beta 3 would change based on the bounds, right? So if beta 3 was supposed to be positive, then the greater that the bounds in x1 is, for instance, the more marginally valuable x2 is for making y bigger, and that changes the overall outcome for the problem, for the minimization problem in this case. Now, if x1 were constrained to be extremely small, then this interaction term wouldn't have much effect, and there'd be a lower marginal increase in y as you change x2. So in other words, constraining x1 changes the effect of x2 on y. A smaller x1 means x2 can have less of an effect on y given beta 3 is positive. A bigger x1, a bigger positive x1, means x2 can have a bigger marginal effect on y. And those changes change the way you take your maximization or your minimization problem. So in general, you have this interdependent issue where they're all connected, and that makes things very difficult under constraints, and we can't just look at the balance, for instance. So we're going to develop a mechanism to rigorously assess constrained optimization problems, and in this module, we're going to discuss the method for equality constraints. Okay, so let's get rid of this. Now, what's an equality constraint? An equality constraint is a constraint, which we'll call G. It's going to be a function of the variables and some constant parameter C. You can think of C as a budget constraint, for instance. An equality constraint says that this constraint equals 0. That's your constraint, the thing's equal to 0. In practice, so using the apples and oranges example, we would have apples plus, one way of writing this would be apples plus 2 oranges. Let's say you had to spend your entire budget equals some budget. Let's call it budget C. We often want to put it in this way of writing it, this format. So we can write this as apples plus 2 oranges minus C equals 0. And we can always do that. We can always set this problem up such that there's some left-hand side, which is a function of the variables, which are here apples and oranges, and the constant, that's like a budget constraint in this case. You can always do that and make the thing equal to 0, and that is an equality constraint. It's an equality constraint because you're constraining some combination of the variables to equal 0. Sometimes you'll see it equaling this, but typically to make the thing work, we always want it to be in this format right here with all the necessary arrows on it. Okay, that is an equality constraint. And then 2 modules from now, we'll deal with inequality constraints, where you replace the equals with a less than or equal to. But we'll deal with that when we get to it. Here, they're equality constraints. Now, as you said in a previous module in this lecture, these are not necessarily incredibly common in political science in general, because oftentimes we have more leeway. We don't have to meet the budget. We don't have to be positive. We can be 0 too. But there are scenarios in which you do have equality constraints. And in particular, as you mentioned there, if you have a budget constraint, but you have non-satiable preferences, you want more and more of everything, then you will always use your entire budget on the stuff you want because you want more of everything, so you spend all you can to get as much as you can. So sometimes we can convert our inequality constraint, our budget constraint, into an equality constraint. But typically we're going to have the more complicated scenario of inequality constraints. But we go through this anyway because this is a necessary first step for doing inequality constraints. Okay, so there you go. So that's the background of why we're doing this. So how do we do this? Okay, we're going to start by adding a variable. Now you're probably saying, now, why do we want to do that, right? We just went through in the previous lecture and discussed how we weren't even going to do this 3x3 case because we didn't want to add variables. That's true, but here we need to add a variable. So the variable we're going to add, well, one or more variables potentially, we'll start with 1, is lambda. It's typically used as lambda, sometimes it's mu. We're going to use lambda here for equality constraints. And lambda is known as a Lagrange multiplier. And the Lagrange multiplier has a bunch of interpretations we'll talk about later. But for our purposes now, the Lagrange multiplier will enable us to incorporate our equality constraint into our maximization problem in a nice way via the construction of something called a Lagrangian function. Here's the thing we use for it. And this is going to equal, right? This is going to equal the original problem So there's an f, and it's going to be some function of variables f. Sorry, variables g rather. X. What am I saying? Function of variables x. And that's the original problem we have. So the problem is, I'm going to deal with maximization here because it's more common, but it doesn't matter. Maximize f. That's how the problem is normally stated. Maximize f subject to constraints gi. The subscript I, and these are all functions of both x and various individual constants. Now, there's a subscript I here because you could have more than one constraint. We generally won't deal with a lot of equality constraints in a row, but you can, in theory, have 100 constraints. You say you have 200 variables and 100 constraints, you get a very messy, very long problem, but you could do it in the same methodology. I would advise you in that case to use a computer, though. So this is the problem you normally get, and you solve it by introducing a Lagrangian and a Lagrange multiplier. Now, the Lagrangian is formed by first taking the original objective function you're trying to maximize, the f, and subtracting for every single constraint the Lagrange multiplier. I have a subscript I again. There's one lambda for every constraint. Each one is a different Lagrange multiplier times the constraint. And this is the Lagrangian, and then you're going to sum this over all the constraints. I'll leave off the bounds because whatever number of constraints you have, that's how big the sum is. Now, why would you do that, right? Turns out there's a pretty intuitive reason you do this, right? You're trying to maximize f, get the biggest f possible. What do those other terms mean? Well, because g equals 0 is the constraint, basically all you're doing is adding a whole bunch of zeros or subtracting a whole bunch of zeros. And you can do that, right? You don't fundamentally change the nature of the problem, right, by adding a whole bunch of zeros to the problem, right? You're just saying, here's my Lagrangian, and here's my original function I'm trying to maximize. And I'm going to add, or subtract rather, a whole bunch of zeros from that, one for every constraint. That changes nothing. It doesn't change the fundamental problem. You're still trying to maximize that f. You're just doing it with a whole bunch of zeros at the end of it, subtracted from it, which changes nothing. But then why do we do it? Well, the method we're going to use to do this, the first step, instead of computing the gradient, we're going to compute the gradient, instead of computing the gradient of f rather, we're going to compute the gradient of the Lagrangian. And we're going to include not only all the components of x, but also all of the lambdas. So this thing is going to look like this. So that'd be the partial of Lagrangian with respect to x1, dot, dot, dot. I'm trying to make dots in this thing. To the Lagrangian with respect to the partial Lagrangian with respect to xm, assuming there are m components as before. And I'll put bounds in this just to be clear now, 1 to n. And then you have the partial Lagrangian with respect to the Lagrange multiplier 1 all the way down to the nth Lagrange multiplier. And this is now your step 1. Basically, you add these variables, these lambdas, and you treat them all as variables you have to maximize. You have to maximize a function with respect to all those variables. Okay. Now, why would you do that? Right. We'll go through much more detail when we see the actual full method written out. But you do this because note what happens whenever you take any of these variables. Remember, step 2 is we're going to set this gradient equal to 0, which means every single component of the gradient vector is going to be equal to 0 by itself, which includes rather all these ones here. Why is that good? Well, where's the only place lambda appears in the entire Lagrangian? Well, lambda 1 only appears multiplying g1. It does not appear in f. It appears only multiplying g1. So this derivative right here is going to equal negative g1 of x, but this is an I, this is a semicolon. Let's put a comma for the future. This. But that's true by definition, right? We know the constraint equals 0. So what we're doing by taking all these partial derivatives with respect to the lambdas is forcing our constraint to hold, forcing our constraint to bind. We say a constraint binds if without the constraint, the variables would be something different than they are at the maximum, right? So if the maximum would produce a value different from a value of g different from 0, then forcing to be at 0 means your constraint binds. The constraint is binding the location of the maximum or the minimum to be to satisfy it. It's forcing to satisfy it, it's constraining it. So a constraint binds when the constraint actually has an effect, has a strong effect. All equality constraints always bind. Inequality constraints might not bind, and we'll talk about that later in a couple modules from now. Okay. But by doing this, what we're doing is forcing each one of these equations in step 2 forces the constraint to bind. So basically, we're independently forcing the constraint to bind using this method. And that enables us to compute these constrained optimization problems. We basically stick on these zeros to our Lagrangian, to our objective function to form a Lagrangian. We take this expanded derivative, gradient, we set them all equal to 0. These things on the bottom will all just produce the constraints back again. So when we solve our system of simultaneous equations, we will be forced to have all the constraints actually bind. Because if they didn't bind, then you would not be able to solve the system of equations, because that particular equation, like this equation right here, would not hold. It only holds when the constraint binds, and therefore you're forcing all the constraints to bind with this setup. But note, this is important, it is not simply the same problem as before with a whole bunch of constraints that are forced to bind, because when you do these things, the actual derivative has an effect on this term too. So take the first one, right? That's going to equal the original partial derivative, which was the original thing we were saying equal to 0, minus lambda, minus the sum of all lambda I, times the partial of g with respect to x1. So for every constraint g sub i, it should be gi here, for every constraint g sub I that has an x1 in it, you would take that partial as well. Now what that gets you is a potential string of terms that are derivatives of these constraints, and that will change the actual values of the x's that you get when you set them equal to 0. It will change the critical points. So this actually will affect the overall outcome, and this is how the first two steps translate into the case of equality constraints. Okay. Now we have to talk about how the third and fourth steps translate, which we do now. Recall that in the case of an unconstrained opposition problem, we're interested in looking at the Hessian and how the Hessian is positive or negative definite. In this case, we're going to do something similar, but instead of a Hessian, we're going to use a bordered Hessian. I'm going to call that B. Now B here is a bigger matrix, sometimes much bigger. A much bigger matrix that basically borders the Hessian, which is going to be in the lower right-hand corner, with derivatives. The second derivative is related to the constraints and the Lagrange multipliers. So first we're going to have that up here, and we're going to have with respect to so for each row of the Hessian in general, and the bordered Hessian too, corresponds to a different derivative with respect to a different parameter. So first we're going to do lambda 1, and this would be lambda 1 again. I'm doing this very deliberately. And then d squared Lagrangian d, partial lambda n. Each row is a different one, so here's the nth one. And then here's the first of the actual parameters, the variables in the model. Dot, dot, down to the bottom here, which is the last of the parameters of the model. We said there were m of them before. Okay. Now going this way, you have all the constraints again. These are symmetric, remember. And then the first of the variables to the dot through to the symmetric thing in here. The last of the variables. That's the end of the matrix, and I ran out of room to make one little end of matrix thing. Parentheses. And then the bottom here, right, you have is just the Hessian itself. Right, this would be x1, x1, and down to dxm, d partial xm. So basically, you get 4 blocks. This block are all partials, second partials related to combinations of lambdas. Now note that looking back at the equation for the Lagrangian, the lambdas never enter in any nonlinear fashion. It's just minus lambda I times the constraint gi. So every single element in the upper left block is 0. There are no second partial derivatives that involve combinations of the lambdas. So this is all going to be 0. A big block of 0. So this is a block matrix. This block down here is the original Hessian. That's why it's bordered. And these are the borders. These are symmetric over here and here. And these are symmetric borders that are the the mixed partials, the cross partial derivatives with respect to one of the constraints and one of the variables. So it'd be bigger than before. Now, we're not going to deal with any cases more complex than a 2-variable, 1-constraint case. Any more than that, you're really going to want to move to a computer unless you really love taking lots of derivatives and solving lots of equations at once yourself. But that's the bordered Hessian. Now it's going to turn out the rules for the bordered Hessian are the exact same as the rules for the Hessian. If the bordered Hessian is positive definite, you have a local minimum. If the bordered Hessian is negative definite, you have a local maximum. So all that's left is to figure out how to actually assess, do you have a local minimum, local maximum, or is the test indeterminate? If it's neither positive definite nor negative definite, it's indeterminate. And that's all we're going to be trying to do right now is the exact same thing we did in the case of unconstrained optimization, but instead of Hessian down here, it's the bordered Hessian, which is bigger. So, how does that work? Now, we discussed one method of doing this before, which was to look at the eigenvalues. We could look at another method here, which is to look at the leading principal minors. Now, what are leading principal minors? Well, a leading principal minor of order k, so say leading principal, and the book has a little more depth in this, but I don't want to take too much time on this one. It's already a pretty long module, and I don't take too much time. It's something that's not going to come up a lot. Leading principal minor is the determinant of the matrix you get by, and that's an n over here, of order k, is the determinant of the matrix you get by eliminating the last r minus k rows and columns, where r here is the size of the matrix. So let's say your matrix is r by r, and I used m in the book, but we already used m for the number of variables here, so we use r. So if your matrix is r by r, then this is the determinant of the matrix you get by removing the last r minus k rows and columns. So the leading principal minor of order 1 is the one you get by removing everything but the upper left element. The leading principal minor of order R is the one you get by removing nothing. That's the determinant of the entire matrix. And so basically you take determinants of bigger and bigger matrices as you get the order higher and higher into from 1, which is the determinant of a single element, to R, which is the determinant of the entire matrix. So that's what that is. What you use it for is to assess the way in which the signs of these minors change. Now, there's a general rule for this, which is in the book. I want to focus on, so not to be overly confusing, too late, not to be overly confusing, focus on the rules for the case of the border Hessian, which has constraints, and thereby has some variation in the rules because there's a 0 out front. So let's start a new thing here to make that clear. So remember, the border Hessian, you can write like this, right? So you have up here is either a single 0 if you have one constraint, or a matrix of zeros corresponding to the second partial derivatives of the Lagrangian with respect to various combinations of the Lagrange multipliers. And since those are all 0, you have a 0 matrix up there. Over here in the off-diagonal blocks are C and C transpose, which are just the matrices corresponding to the cross partials of the Lagrangian with respect to the Lagrange multipliers and variables. And down here you have the Hessian. So if you write it this way, it kind of illustrates why we're not going to actually go through and give the general rules for how to compare, how to look at a matrix and determine from its leading principal minors whether or not it's positive or negative definite. It's given in the book, but rather than give you two different rules here, which might be kind of confusing with all this stuff already being thrown at you, I'm instead going to give you the rules only for a border Hessian, which are simpler because, if you note, all these leading principal minors are 0. They're just 0 matrices, so the determinants are all 0. So why bother calculating those or including them in some rule? Similarly, the next one looks like this: a 0 matrix, and some x, and some other x, and whatever, something, right? The determinant of this is just negative x squared. So that's always going to be negative. So basically this matrix up here, if there are n constraints, is an n by n matrix. We can ignore that, and we can ignore the next one as well. So then n plus 1 principal minors can all be ignored. So rather than consider them, we're going to have rules for just the second part. Okay, the rest of them. So now remember that m is the number of variables, and n is the number of constraints. Let's say constraints, but I ran out of room, sorry. Now, what we know is that the rules are we have to consider only the m minus n leading principal minors. If m is, again, 2 variables, and n is 1 constraint, which are the only kind of examples we give in the book and in the examples in the next module, then 2 minus 1 is 1. We only consider the last leading principal minor. The last leading principal minor is the determinant of the entire thing. But if you had more constraints and more variables, then you would have potentially more, you must consider more leading principal minors. So if you had 3 variables and 1 constraint, you'd have 3 minus 1, or 2 leading principal minors to consider. So that would be the whole bordered Hessian, and the bordered Hessian you get by removing the last row and the last column. And so on and so forth. If you had 4 variables and 1 constraint, there'd be the last 3 leading principal minors. So you would remove, you do the whole Hessian, the whole bordered Hessian, the last row, and the second to last row, and so on and so forth. Okay. So given that, here are the rules. If it's the bordered Hessian is positive definite, if all the last m minus n leading principal minors, this is last, just to be clear, last ones, and then the last one is always the full one. If all the last leading principal minors have the same sign, and I keep dropping the lows, have the same sign as -1 to the n, where n again is the number of constraints. So if you had 1 constraint, you should have all the leading principal minors be negative. And if you only had 2 variables, you only care about the full matrix anyway, the full border Hessian determinant anyway, so the determinant should be negative in that case, if you had one constraint. Okay. Negative definite's a little trickier. Negative definite, if first of all, the last leading principal minor has the sign -1 to the m, so if you have two variables, you should have a positive determinant. If you had one variable, if you had three variables, you should have a negative determinant. And all of the last m minus n leading principal minors alternate in sign. So if you had three variables and one constraint, you could have the last two leading principal minors. Then you should have that, first of all, the determinant is negative, because -1 to 3 is negative. And then the next leading principal minor, the one you get by removing the last row in the last column, should be signed positively. So they must alternate. So those are the rules. And again, they may not be the most intuitive things ever. That's the reason actually in Module 1 we discussed rules using eigenvalues. They strike me as much more intuitive because they give you sort of central characteristic factors of these matrices. But these principal minors are related, and they can give you a way of calculating more quickly in some of these cases what the whether or not the B is positive definite or negative definite. And if neither of those two things hold, it's indeterminate. So this is what you can do there, and you can use this just to figure out whether or not your border Hessian is positive definite or negative definite for the same reasons as before we did for the Hessian, to figure out the local curvature, in this case of the Lagrangian, around the critical point. Okay, so now what we're going to do is go through and list the rules out in detail, just basically repeating what we've done before, but putting it in rule form, in numerical form, and then we'll talk at the very end and give you a little more intuition behind this stuff to give you a little further subsequent incentive and justification for why you went through all this long module. Okay, let's do that now. Okay, so the first step is to write all your constraints in the form that we looked at earlier, which is write all your constraints like this. So whatever constraint you have, be it a budget constraint or anything else, transform it into this form where you have some function of both x, and oftentimes you see that C dropped, so some function of x and some constant, and set that whole thing equal to 0. So write all your constraints and set them equal to 0. Okay. 2, form the Lagrangian function. That will equal your objective function minus the sum of all your constraints times the Lagrange multiplier associated with that constraint. So again, step 1, make your constraints such that they all equal to 0. Step 2, form the Lagrangian by taking the objective function f, the original thing you're trying to maximize or minimize, and subtracting the sum of all your constraints, each multiplied by the appropriate Lagrange multiplier lambda I. Because each constraint was 0 from step 1, all you're doing is subtracting a whole bunch of zeros. Those are the two additional steps from before. Everything else is basically what we've done before again. So step 3 is going to be finding the gradient of the Lagrangian. Step for all, note, include all x components and lambda components. Step 4 is the old step 2, which is set this thing equal to 0 to find not only the critical points x, but also the critical points lambda. Right? So again, you just find the critical points, but now you have to include the lambdas as well. Step 5, compute the bordered Hessian at each x star lambda star. Step 6, use leading principal minors or some other method to determine if you have a local max, and that's if you have a negative definite B, a local minimum, and that's for a positive definite, that's an S, positive definite B, or if or indeterminate. Okay, and then step 7 is answer 4. For each one of these critical points you have, compare the values to see what the global minimum and the global maximum are. And that's it. That's the method. It's exactly the same as the previous method with 2 steps added up front to get your original problem in the form of a constraint optimization problem. So setting your constraints equal to 0 and then forming Lagrangian. You go through all the rest of the stuff, replacing the function itself with Lagrangian and the Hessian with the border Hessian. But that's it. That's the technique. And that's most of the intuition, frankly, too. But before we conclude, I just want to add a couple more little bits of intuition that might be helpful. Specifically, what is lambda? What are these Lagrange multipliers? Well, let's think back to how we defined our constraints GI. We wrote them pretty quickly like this. But in general, there were things like budget constraints, right, in which you had some function of the variables, and that had to equal, constraint to equal some constant, right? So then this thing has to equal h, speech of I, I guess, minus ci, right? So by splitting it up, we can get a handle on what these things mean. They occur in the Lagrangian multiplying lambda I. So lambda I, negative lambda I gi is equal to negative lambda I hi x plus lambda I ci. Now what happens if we took the derivative? And that's the only place they appear is in these g's, right? There's no other appearance of these c's anywhere in the function in Lagrangian except for multiplying, except for as part of g, multiplying lambda. So the derivative, the partial of the Lagrangian with respect to ci is just, that's an I, not a negative sign, is just lambda I. These things sometimes are therefore called, these Lagrangian multipliers are sometimes called shadow prices of the constraints. The reason is, as you vary the rate of change in the utility, lambda, sorry, the Lagrangian, right, the rate of change in the utility you get as you vary the constraint. So they basically tell you the cost of the constraint, right? The bigger the constraint is, you're going to have a lower overall utility. So they tell you that rate of change in the constraint and the utility with the constraint is lambda. So they give you the sort of the shadow price of the constraint, how much the constraint costs you in terms of lost utility. And remember the opposite. Gave you back the constraint equaling 0. So this equals the constraint. When we set equal to 0, you get the constraint equals 0, right? So both of these derivatives are helpful. This one occurs pretty essentially when you are calculating the steps of the constraint optimization problem. This one helps you with some intuition. If you don't like this intuition, we can do one more thing for you. Let's do it graphically. This is a very typical thing you would see in an econ text. Here are 2 variables, x and y. This line here, assuming you can subdivide x and y, represents a budget constraint. So you might have enough to buy this much y with no x, or this much x with no y. And the line is a combination of various parts of x and y that add up to, in cost or whatever, some budget constraint. Now you have utility as well. Say utility looks like this for x and y. Each one of these lines then is an indifference curve. Remember we talked about indifference curves before. An indifference curve is just a curve along which utility is constant. You're indifferent between any point on that curve because utility is constant at any point. You could draw a whole bunch of these, and again, as you get closer and closer to 0, your utilities are decreasing, right? This over here is a bigger utility than this over here because you're using more of both of them and you like both of them better, so you have more utility there. So as you get closer to 0, these are smaller and smaller utilities. Why am I doing this? Well, really what you care about intuitively is you want to get the maximum utility you can while still satisfying the budget constraint. Well, where's that? That's the point at which the utility curve is tangent to the budget constraint. That's almost tangent there. So this point right here the point of its utility curve, I'll draw that in red, the point of its utility curve is tangent to the budget constraint, is your point of greatest utility. Why is that? Well, if you drew a curve, if you drew the next utility curve down, then you could get more utility by moving up towards this way. And if you drew the next utility curve up, this one over here, the one I'm now going to draw in blue, this one over here, you can't actually afford that much utility. So the point at which your utility curve your difference curve just is tangent to the budget constraint is the highest utility. That curve that's just tangent is the most utility you can get, represents the most utility you can get, and the point of tangency will be your optimum, the set of x and y that give you the highest utility, given your budget constrained by your budget. And that's it. That was a very long module, but I hope that gave you a sense of how to go about doing these things and why this and the intuition behind trying to do constraint optimization for equality constraints. The next module, we will use the technique we just did to do a couple of examples. Again, there are more examples in the book and so on. Thank you very much.